Okay, let's get started. We are going to spend a couple minutes just talking about deliverable 1 and deliverable 2, and then we'll jump back to lecture. Let's see, how are things going with deliverable 1? Most people over installation headaches, more or less? Yes?
Was it not configured to run on PCs at first? Because I got that. No. I spent like 4 or 5 hours. I've basically memorized that code.
You may have noticed that I have a Mac, and as you can probably imagine, I wrote the deliverables on my Mac, so yes, people that have Macs are probably going to have an easier go of it, generally speaking.
After 12 and 13, should we anticipate more problems?
After steps 12 and 13?
Yeah, because I mean, I've spent,
famous last words. I
I've
think
spent 2
once
days
you
on
get
that part,
okay.
so I get stuck on something else. Because you can't progress until...
Right. If you manage to get the Leap Python SDK installed and matplotlib running, you're probably 99% of the way there. I can't promise 100%, but that's the bulk of the challenge.
I'm on Windows and I had the same issue, and after that, it's fine.
So what was the particular issue with Windows?
It would only draw your last point.
Oh, it would only draw your last point, that's right. So someone sent me an email about that, and I put it up on Blackboard. So there's a Blackboard announcement for those of you that are on Windows. So hopefully if it's worked for 2 of you.
Figured that out. I put that code in, and it worked perfect. So
excellent. Who put that code in? Scott. Thank you, Scott. Okay, excellent.
It was happening on Macs too.
It was happening on Macs too?
Yeah.
Okay. So if you're still having that problem, try and put a pause statement in there that gives matplotlib a chance to catch up. So matplotlib was originally designed for creating static visualization, so it's kind of a hack to make it run interactively in real time. I apologize for that. Okay, Scott, you've identified yourself now, so all PC problems go to Scott. No, just kidding. Okay.
Well,
all right.
Because now I'm stuck on a different problem and I can't find a solution to it, so I might have the best plan.
Okay. Anyways, send me your woes, and at least if I can't answer them, I'll put them up on Blackboard, point you to the TA. We'll get there. All right? Okay, so again, deliverable 1 is going to be due next Monday. Hopefully, as you all know, Monday is a holiday, so no class on Monday. Deliverable 1 is still due 11:59 p.m. on Monday. Typically, I introduce the new deliverable on Monday, but since we're not going to be here on Monday, I'm going to talk a little bit about deliverable 2. It's assigned. I haven't made the link there, but I forgot to add the link. I will add it when I get back to class. Deliverables 2 is there. If you want to get started on it now, that's fine. But as usual, deliverable 2 will be due the following Monday at 11:59 p.m. Okay. So let's talk about deliverable 2. So in deliverable 2, let me find the screenshot here. Let me find the video. In deliverable 2, you are going to be translating your, don't ask me this again, you will be translating your 2D visualization into a 3D visualization. So we're still going to be using the interactive real-time matplotlib visualization, but instead of drawing a 2D plot, it's going to be drawing, hopefully in real time, a 3D plot, and you'll be able to draw your hand in 3D in real time by the end of deliverable 2. There is, I believe, a couple of videos for this one, yeah. So you're still making a playlist. I think there's 2 videos in this one. Same deal as last time. Create a new playlist, add the 2 or 3 videos, and submit a URL that points to the playlist as your submission for deliverable 2. Okay, let's just have a look at step 11 here. So the big change from deliverable 1 to deliverable 2 is we're going from 2D to 3D. And also, instead of grabbing just one set of 3D coordinates, which is the tip of the index finger, now you're going to grab the coordinates of all the bones in the hand. So you can sort of see how this is going to go. Like in deliverable 1 in 11a, you grab a frame and you, assuming there's a hand over the device at that point in time, you grab all of that data. It's stored in the hand data structure. Then you iterate 0 through 4. So in Python, the last element in the index there is not counted. So 0, 1, 2, 3, 4. You're iterating over all the 5 fingers in the hand. So you're going to have to pull out on line C there all of the data corresponding to the ith finger. Then there's an inner loop, J, which is going to iterate over the 3 bones in each of the finger. So you can see on line E here, we're grabbing information about the jth bone in the ith finger. And then remember that every bone is a cylinder situated in 3-dimensional space, so it has a 3D coordinate describing the base of the bone and another 3D coordinate describing the tip of the bone. So you're going to be grabbing those 2 coordinates, those 2 sets of 3D coordinates, the position of the base of the bone, the position of the tip of the bone, and now you're going to be drawing a line that connects those 2 points in 3-dimensional space, right, which will give you the wireframe hand. Okay, in step 11 here, I put a handy a link to some documentation here. This is very helpful. So I kind of misspoke last time when I said there are 3 bones in your hand. There are technically 4, but we're only going to focus on the 3 outermost ones, the distal, intermediate, and proximal phalanges. Okay. Okay, so this is a good reference as you start to try and figure out which bone and which finger you're working with. Okay, any questions about deliverable 1 or 2? No? Okay, so let's jump back to lecture. We're working our way through our first theme here, introduction and overview. We're going to jump back into lecture 2 in a moment, which we should finish today, and we'll probably get partway through lecture 3 today. Okay, so we ended last time by thinking about people and computers, which are obviously going to interact, and thinking about the similarities of people and machines. Both receive input along different input devices. They do a little bit of information processing and then produce an output. Here's a list of some of the things we talked about last time. Just as a reminder as we go through, remember to annotate these red boxes as we go. We mentioned a lot of these elements last time. And as I ended last time, this is pretty much where the similarity between people and computers end. What are the differences between these 2 sets? How do people and machines differ in terms of how they receive information and how they affect their environments?
One obvious thing that seems apparent to me is that humans really do have a finite set of inputs, whereas computers, the number of inputs really can develop as time goes.
Absolutely, right? So our set is pretty much fixed. We used to have more input devices than computers. That's probably not true anymore. What else? What's different between human and computational input devices? Your senses and the way in which your computer receives information.
We process analog data, while computers digital.
Absolutely, right? So all of our input is analog, more or less of some signal. Most of computers' input is digital. A lot of the input devices are becoming more continuous and real time, but usually that's downsampled to a digital signal in some way, right? An important difference. What else? What about the output side of things?
We only have 1 output.
We only have 1 output, right? Mother Nature has been very clever in adapting that output device, our muscle, to accomplish lots of different things. The ways in which computers are able to affect their environment is growing, right? For quite a while, it was just a printer. Then it was printers and monitors. Then it was printers, monitors, and speakers. Then it was vibration. And now that we get into embedded devices and robots, the way in which computers can directly impact the physical world is growing, right? For better, for worse. Okay. Okay, so humans, at least for now, maybe have more input channels. Most of our input is continuous. Computers are digital. Another major difference that we're going to see as we go through this course is humans are very good at manipulating our output device or moving in certain ways to expand or focus our input devices, right? We are not purely passive. We can act to change the ways in which we receive information. What are some examples? So I can see most of your faces, but some of the people that are sitting in the back of the room, I can't see your face too well. If I want to, what do I do? In order to rectify that deficiency in my visual stream, I move, right? It seems trivial, right? It seems not worth talking about. Computers cannot do that, right? If the webcam is on here, the best the computer can do is maybe send me a signal saying, can you please move me so I can see something else, right? Computers are not very good at using their output devices to change what they can sense in the real world. We do this all the time. You're not always aware of it. What else? How else do you act to broaden the information that you're receiving from the outside world? So there are very mild air currents in this room, which you may be able to detect. Not very well, though. What might you do to try and figure out how air is moving in the room? Lick your finger and hold it up, right? Maybe that doesn't work here so well. There's sorts of those kinds of things that we do all the time, and again, you might not be aware of it, right? So exploiting your interaction with the physical world to extract more information from it. In a fundamental sense, most of our traditional computational devices, laptops and desktops, and even these things are pretty passive, right? They're at the mercy of their human operator to get information from the outside world. And again, with embedded devices and robotics, that's changing. We're starting to see new technologies that are able to move or act in the world to get the information that they need, rather than having to passively wait for someone or something to give it to them. Okay, so I started with sort of this tongue-in-cheek cartoon of people as sort of this passive thing that sits there and gets information from the world, cogitates, and outputs. The reason I started with that is that has been, until relatively recently, a fundamental assumption in human psychology. And we're going to go back now a little bit into the past to B.F. Skinner, where this idea came from. Before Skinner, in psychology or the study of human behavior, it was basically going out in the field and observing animals or humans in their natural environment and telling anecdotal stories about what they did, right? Which was fine, but it wasn't very satisfying if you were an empirical scientist and you wanted to try and quantify and understand animal and human behavior. Let's say you have a particular animal species in mind and you'd like to know, is that animal capable of learning or not? You might send some field scientists out into the field and they would observe the animal and say, well, it seemed to be doing this and it changed its behavior on this day compared to this day. It wasn't very satisfying, right? How could you try and prove or show quantitatively this species is capable of learning, this one isn't, this one is capable of this, and so on? Skinner said, let's be done with it, forget about the wild, let's try and reduce and control the kind of input that an animal receives, and also reduce and control the kind of output the animal can provide. So Skinner invented what came to be known as the Skinner box. You would put the animal in a box, provide some sort of controlled stimulus, so you could turn on and off a light, emit a sound, supply some food, supply some air, supply some water, and so on, in a controlled way. And maybe you allow the animal to turn one or more of two levers. The moment you place an animal or a human in a Skinner box, it changes the way you think about that animal, right? That animal is receiving some input, and you're observing how the animal reacts to that output. Okay, so here would be a typical experiment with operant conditioning. We put pigeon, in this case, in the box. And from time to time, we shine a light. And if, when we shine the light, the pigeon pecks lever 2, and only lever 2, we give the animal some food. That's an experiment we could conduct with the Skinner box. How would that experiment allow us to tell whether the pigeon is capable of learning? What would we expect? What would be your prediction of the outcome of this experiment?
Next time you shine the light, it would peck lever 2 again.
Absolutely, right? So if this animal is capable of learning, it should learn, it should peck lever number 2 more often when the light is shone as time goes forward into the future. What happens if it doesn't? Can we conclude that the animal is incapable of learning?
We conclude that it doesn't respond to that stimulus.
It doesn't respond to that stimulus, right? So it doesn't do what we want in this particular situation. Okay, so again, this isn't a psychology class, but just to sort of lay some context here, we have this sort of bias to think of animals and people and ourselves as sort of this thing that is waiting for input, and when something happens, the animal or the human reacts, right? So social psychology and anthropology sort of has followed along in the footsteps of the Skinnerian view of behavior and sort of observed humans in the same light. The Skinner box was introduced in about 1930, and around the same time, someone else on the other side of the pond, Alan Turing, introduced this thought experiment of a hypothetical machine, which in 1936 only existed as a hypothetical thought experiment, the Turing machine. Anybody want to hazard a 2 or 3 sentence summary of how the Turing machine works?
It's an infinite tape that can go left or right. You can either read or write through each piece of tape as it goes.
Exactly, right? So here's our Turing machine. Either the tape moves or the machine moves. So it's capable of output. The machine, let's assume it's the machine that's moving. The machine can choose to stay still, go left or go right. So very, very simple output. It's also capable of erasing and writing a symbol to the segment of tape in front of it. It has input. It can read the symbol, and it can decide what to do, what action to take given the current input. What's the current symbol on the tape? Compare it to perhaps internal state, and then act, right? So before computers even existed in the thought experiment that came to be known as Turing machines, right, there was already an assumption that these kinds of machines would take some input, they would think, quote unquote, and then they would do something. It's interesting that the Turing machine was introduced in 1936, 6 years after Skinner introduced the Skinner box. Whether Turing was influenced in his thinking about how these automatic machines would work, whether he was influenced by the Skinnerian view or not, it's not clear. It's kind of interesting to think about. Okay, so it's not surprising that we tend to think of people and animals as input, processing, and then output, and we now have physical devices which any computer existing today is just a physical manifestation of this, right? It's a fancier version of a Turing machine. So people and computers take input, they process, they produce output. Okay, instead of going forward in time, let's actually go back in time to 1896. Let's talk about John Dewey. The grave, here's a picture of John Dewey's grave. Does anybody know where this tombstone is? Absolutely. So if you have time after class, or if you have some time between classes today, on the far side of Ira Allen Chapel towards Colchester Ave from us, you can go visit John Dewey's grave. He was a UVM graduate of 18 something or other, I can't remember. Went on to do great things in philosophy. And one of the cornerstones of his thinking about philosophy and also about the philosophy of education was that students should not sit passively and receive information. Unfortunately, that's still what happens most of the time. Dewey argued that we are not passive entities. So we do not begin thinking with a sensory stimulus. We're not sitting there waiting for sensory input, but rather we have a continuous feedback loop with the environment, right? So Dewey tried to demolish this idea of linearity of thinking, which existed long before Skinner and Turing. So for Dewey, we were not these passive machines that received input, then thought, and then acted. That arc going from perception to thinking to acting is known as the reflex arc. He said, forget about the arc. The arc doesn't exist. Instead, it's a feedback loop. So for Dewey, he called this sensory motor coordination, right? Sensors and motors, or your senses and muscles. You're in this continuous real-time coordination with the environment. If it's a feedback loop, how can you talk about sensory first, then acting? There is no sequence. It's this continuous process. Okay. Moreover, for Dewey, he said, it's not really the sensing which is primary, it's the movement, right? As you exist as a physical entity in the world, you're breathing, you're thinking, you're acting all the time, and when you act, there is a sensory repercussion to your action, right? You finish your ASL educational software, you plug in the device, you put it in front of someone, they will immediately start interacting with it, and they will probably disregard whatever's on the screen. If someone has not seen the Leap Motion device before, they might grab it and try and move it around like a mouse. They will start acting or interacting with your software and hardware, and they will observe the sensory repercussion of that action. When you try this out on your roommates and so on, watch what they do when they interact with your system for the first time. Typically, they will act and observe the result of the action. Right? So Dewey said, if you want to really think about interaction, or in this case, human behavior, flip things around. And it's much harder to do. It's less intuitive. Think about action and sensory repercussion, which is an active process, rather than sitting and waiting for sensation, then thinking, then acting. Okay, so we're going to try as best we can throughout the rest of this course is to take a Deweyan approach to behavior rather than a Skinnerian approach to behavior. We're going to try and think about people interacting with our software before we've ever written it, and we're thinking about how they're going to click the mouse, tap on the keyboard, wave their hand, grab the device, and how our system should respond to user action to help the user understand what is the feedback loop you're trying to establish between your user and your system. Okay, so this is the case, right? We have this continuous real-time analog interaction with our physical environment. We start out in the first few years of life doing a lot of that, grabbing objects, putting them in our mouths, trying to break things, hammering on our younger brother and sister, learning about what happens when you act on the world. How does the world respond? After a few years of life, you realize that you're not the only human out there. There are other things out there like you that are also doing the same thing. So we get these expectations about our interactions with the physical world. I expect that usually if there's something far from me that I can't see very well, generally speaking, if I move, I'll be able to see what's back there. Doesn't work if you're looking at a computer screen, right? But most of the time in the real world, that's a common expectation. We then, as we become more social creatures, as we grow up, we also have expectations about social interactions, right? So if I ask a question and then pause, I expect after a few seconds of you thinking about it, you might offer me an answer to my question, right? So we all bring to any new software system years of experience about what happens when we physically interact with the world and what happens when we socially interact with the world. And some of those expectations are implicit, right? If I see something that looks like a mouse plugged into the computer and I grab it and move it, I expect something on the screen to move in more or less real time. I don't know if you've ever experienced it, but there's sometimes if you grab a mouse and you move it and there's a little bit of a lag, so the movement is like 1/10 of a second off from the movement of a mouse, it is the most frustrating thing possible. Another way to frustrate your expectations about interactions that come from the real world, take your mouse, if you have an external mouse, turn it 90 degrees and now grab it and try and move the cursor to something on the screen, it's very, very difficult. Why? Because if I grab something in the real world and I move it this way, I expect to see the thing move in real time along with the action. Right? That's a common expectation we've built up from the physical world that we expect to see when we manipulate a mouse and a pointer, right? If that expectation is broken, your users get frustrated pretty quickly. So a lot of this course is going to be trying to identify those expectations that we have about the physical world and the social world and making sure that we're supporting them in our new software system rather than frustrating them. Okay. All right, so now trying to think like Dewey here and think about a constant interaction. What are we trying to do in HCI? Well, we're trying to create this coordination among this pair, right? This human-computer pair to achieve something that would be difficult or impossible through either alone. So let's take a kind of classical human-computer interaction. You sit down at your browser, and you as the user have a particular goal, which is to try and create a new energy policy for Vermont. So you start doing some browsing and Googling and so on. You started out thinking that biofuels was going to be the way to go, but after a little bit of interaction with your computer and browsing and research, your ideas start to change, and perhaps you focus more on solar, despite the fact that Vermont is not ideal for solar. And eventually, the output of this continuous interaction between you and, in this case, a browser, you get a new Vermont energy policy. Okay, kind of straightforward. Think about this human-computer interaction now. So now it's a person with a cell phone. The person starts by acting. So following Dewey, right? Let's think about the person. So you're always doing something. As you're acting, your device is sensing your actions. So your output becomes the input for the computer and vice versa. Right? That's closing the feedback loop. So as I move down the street, my GPS-enabled phone detects that there's a Starbucks coming up, and it also detects that I sent a tweet a couple minutes ago that had the word caffeine in it, and my app infers that perhaps I'd like a cup of coffee. So it buzzes my leg. I access the phone. It says there's a Starbucks nearby. Without me entering anything to the app, I change direction, and my GPS-enabled phone sees that I'm now moving towards the Starbucks and infers that I'm going to get a cup of coffee. It infers that I'm heading to go get another cup of coffee, but now infers that there's only a bar left on my battery. I was heading home, but now I'm heading to Starbucks. The phone realizes that the phone's going to go dead before I get to Starbucks and then get home. My phone, again, infers that I would prefer to have a functioning phone than a cup of coffee, sends me a second message letting me know that I'm going to have to make a choice here, right? So again, kind of a cartoon example here, but we have this continuous feedback loop where it's not as structured as this one, right? It's not the human coming in with something they want to do and going through this process and there being a clear output. Where does the goal and the change of goals and sensation and action start and end, right? It's much more continuous and fluid. So with the introduction of smartphones and more real-time interactive technology after more than 100 years, right? HCI designers have to think more along the Deweyan line than the Skinnerian line, right? We are not inside a Skinner box. You are continuously acting in the world, and the cloud of interactive technology that surrounds you has to try and infer what you're doing and what you want to do and enter into that continuous feedback loop. Okay, so in that little cartoon example, you might believe that the app is doing the right thing or maybe the wrong thing. So if you do go out and design software for a diverse user base, you're going to have users that have very different views of computers. Obviously, if you want to put people and computers together, we would like their respective skills to complement one another. If you ask people that are machine-centered, who like computers, to describe people and computers, you'll typically get descriptions like people are vague, disorganized, distractible, emotional, illogical, and so on. And machines, thank goodness, are precise, orderly, undistractable, and so on. If you ask people that are not big fans of computers, you'll get a very different description, right? The opposite one. Now, it depends on context. Of course, these are all true. So we would like, again, to try and marry computers and people together so that computers are doing what they do best and people are focusing on what they do best. Okay, this is an excerpt from a book by Donald Norman, Things That Make Us Smart. Dr. Norman is one of the founding fathers of HCI. He's written a series of great books about HCI. If you're interested, go have a look. Okay, so throughout the rest of this course, I'm going to try my best to not talk about computers, but talk about interactive systems, right? We're going to try and take an inclusive view of technology that is increasingly, continuously interacting with us. So an interactive system could be a computer, it could be an embedded device, it's a sensor that's sensing whether there are people in the room and keeps the lights on when there are people in the room, and it turns off the light when there aren't people in the room. And a moving embedded device, otherwise known as a robot, something that is able to move itself in the world, and the moment that the robot moves, its sensory information changes. Okay, so again, you're going to see this cartoon over and over again in this course. We've got a human that is interacting in a feedback loop with technology. We're going to assume that interactive systems are systems that enter into this continuous feedback loop and are also processing information in some way, right? So there's some electronics in there. You could argue that your knapsack is also an interactive system. The moment that a person puts books in the bag and puts it on, the weight of the bag changes, which the person senses and does something and so on, right? So the physical objects in your world also enter into a real-time sensor-motor coordination loop with you. We're not going to focus on those. We're going to focus on those that are able to sense this interaction and influence this interaction in some way. Okay, that's an interactive system. I think next week in lectures 4 and 5, we're going to start to get into the design aspect of HCI. So we want to try and think about how people might interact with our hypothetical system. How does that influence the way that we go about designing that system? Right? How do we design a system where we have to think very carefully about who's going to use it? Right? We talked on Monday about leap motion. For this particular demographic, most of you are righties, and most of you are male, and most of you are fair-skinned, right? We've already started to think about people, and that should influence the way you think about designing your software for the leap motion device, right? How do we make that design process a systematic process? Okay. It's a lot of fun because it draws on a lot of different domains. So if we're going to put people first, we want to draw on people-centric domains of knowledge. So we want to draw on sociology. How do people tend to interact with each other socially? That's pretty important when you're developing social media. Psychology. How do people in isolation think? If I reach out and do this, I expect this sensory repercussion, right? How do we get a handle on that? We'll think about ergonomics, right? How people tend to like to interact with physical objects or electronic objects. Anthropology will also become important, right? Somebody mentioned last time that not every culture reads from left to right. That's very important for a lot of the software you might develop, even if there isn't text in your system, right? You throw up some visualization, most English speakers will scan it in a Z, top left, top right, bottom left, bottom right. Non-English speakers, depending on your native language, will not scan your visualization in the same way. Okay, so we're going to draw a lot from human-centric domains of knowledge when we start to think about how to design these systems. We're going to focus in this class not on the back end of the software, but more on the front end. So for the project for this class, the first 10 deliverables, you're going to be focusing quite a bit on the back end so we can get everything working. And then in the last 4 weeks of class, when you develop your educational software, you're going to be focusing on the interface, and that's what you're going to be assessed on. So technologies that are brought to bear in HCI, obviously this isn't purely software. If you're developing something like leap motion or Google Glass or 3D printed prosthetics. You need to think about the hardware as well. So there's a lot of engineering branches involved, multimedia, databases, sensors and actuators, right? How does your interactive system get information from the world and project or influence the world in turn? Programming and networking, and so on. I listed software engineering on the list here. There's a sister course to this course, which is software engineering. Who is taking software engineering or has taken it? Just a couple people. Okay. If you like this course, you might want to take software engineering, which focuses on how to develop the back end of systems. Okay, we're going to look at design in lots of different fields as we go, because obviously if we're focusing on the interface, we can't focus on just the objective aspects of the system. We also have to focus on the subjective aspects, right? Is it a piece of software that the user actually enjoys interacting with? So there's an aspect of aesthetics and ergonomics here. So we're going to look at interaction design, engineering design, graphic design, product design. We already talked about visualization last time. Finally, if we're designing software for people, we need to think about what are those people doing, what's the activity they want to get done, and what is the physical and social context in which they're going to do it. So we're going to think about business soft systems, organizational psychology, communities of practice, tribal knowledge. Tribal knowledge is a good example. I just added that one in red. It might not be on your slides. Who knows what tribal knowledge is? So communities of practice are groups of people that either work together or, in your case, study together. This particular class is a tribe. There is some tribal knowledge among this particular tribe. Tribal knowledge is usually the ways in which a group does what it does, and those rules are not written down. What would be an example of an unwritten rule that most of you are following right now in this class? Writing that down, okay. What else?
Not yelling at each other.
Not yelling at each other, okay, right? So general rules of civility. Aside from general social rules about being polite, what are some specific rules that you're following when you enter or leave this class, or you're in this class, that are specific to being in a classroom?
We're all sitting down facing forward.
Yes, okay. Which, again, the chairs are arranged for you, usually facing forward. Again, that's not written down, so that's a general assumption. You could, if you wanted, move the chairs around. Usually you don't. What else? It's tricky, right? Because even being asked, it's not quite clear, although you follow it all the time. You follow these rules all the time.
Focus on you.
Okay, hopefully you focus on me, most of the time at least.
We generally sit in the same seat.
There it is, right? I've taught this class, I don't know how many times, every class I've taught, generally speaking, most of the time, most of you are sitting in the same seat. No one told you to do that. It's a general assumed thing, right? It's pretty specific to classrooms in the Western world. Why? Who knows, right? It just is. If I was going to write, let's say I was going to write some software for a camera that was going to try and take attendance for me rather than doing it manually, it might matter when I'm developing that software to design that software with the assumption that most of the time you're sitting in the same seat, but not all the time. Right? It may or may not matter, but it might be important. Right? If you go out and design a combined hardware and software system for a company or a nonprofit or some group, some community of practice, you don't know those rules, right? You might, if you go and sit in on meetings or whatever it is that they do and observe very carefully what's happening, you might be able to catch some of these unwritten rules. And it's also hard to explicitly elicit them from the group, right? Even asking you explicitly, it takes a while to get the answer. You tend to sit in the same place, although you all do it probably in most of your classes. Right? Very tricky, right? This is very far from sort of traditional computer science where you're trying to work out all the bugs in your code, right? This is a much more social procedure. Okay, so what are people doing? What context are they doing it in? Are they able to tell you what they want to do, how they generally like to do it, and so on? And how do those things impinge on the way you design software for them? Okay, I mentioned this already, but in HCI, we sort of have a foot in two camps. Psychology, where we're going to draw most of our theoretical base, our concepts, where we're going to start, and software engineering for our design approach. How do we systematically develop software to support our identified group of users? And the user interface is where these two things meet, and that's where we're going to focus. So most of the things we're going to talk about in this class, and most of the code you're going to write for this class, you need to be thinking about these two things, right? How might somebody interact with this? What might they expect my software to do when I do this, or I do this, or I do this, right? Okay. We're going to, as we go, continually unpack what we mean by interaction. We're going to start by breaking it into 3 different kinds of interaction. When someone is interacting with a software system, they are interacting at different levels, at different time scales. The most obvious one is physical interaction. Right? You take your lead motion device, put it in front of your new user, and you can obviously see what they do physically. Do they grab it? Do they wave their hand? Do they sit passively waiting for something to happen on the screen? What sorts of physical interactions do your users enter into? Also somewhat obvious is perceptual interaction, right? Thinking about what the person sees or hears or maybe feels and how they react to it. Or again, turning that around, what do they do and what sensory repercussion are they going to get? Or what kind of sensory repercussion should they get? Third kind of interaction we're going to talk about is conceptual interaction. And basically you can think of this as expectation. When somebody sits down in front of a web browser or the lead motion device or they put on Google Glasses, even if they haven't used that technology very much, they're bringing lots of expectations to bear on the system. So they're thinking about, is the system on? Is it even listening to me? Is the system sensing me? Right? We build up all these expectations. They're building up a prediction about what the machine is doing, right? It's either preparing to show me something, it's number crunching, it's off, it's broken, it's working intermittently. We're making all these predictions all the time about what the system is doing. The field of neuroscience is increasingly coming around to the view that what the brain is a prediction machine. Again, going back to John Dewey, what the brain is doing most of the time is making predictions about what will happen if I do this. Right? You put a person down in front of your interactive system, they will immediately, explicitly or implicitly, start making predictions about what will happen if they interact with the system. And if what they get back differs from their prediction, they're either going to go use somebody else's software, they're either going to find it interesting and want to learn more, who knows, right? Okay, so obviously your interactive system is going to have to provide some sort of feedback to help people build up an understanding of what is the feedback loop here. What is the software receiving from the human and what is it providing back? What are some examples of software you know of where visualization is done well or done poorly, in the sense of visualization that's communicating to you what the guts of the system is doing? What are some common visualizations that are out there?
So if you're interacting with a website, you click a button, it needs to do some sort of processing, and it'll have some sort of like time indicator, like a loop or something.
Absolutely, right? So some kind of loop. There's another great visual metaphor, right? Most of us understand that anything doing this means, hold on a second, I'll give you some more feedback in a moment, right? It used to be an explicit clock, now it doesn't need to be anymore, right? That looping signals or advertises that interaction. What else? It's a common one.
When you like mouse over something that is a button, it'll like react in some way, maybe like moving it's going down or.
Absolutely, right? So mousing over something is you signaling to the system, I want to focus on this thing somehow. And most software systems these days will say, I hear you. I know that you're now interested in this part of the screen or this part of the virtual world or the game or whatever. It will highlight, depress, it'll open a text box, something, right? It's signaling back to you that it knows that you're attending or paying attention to that part of the screen. Sometimes that's great, sometimes that's not. You don't want to have an interactive system where you scroll a pointer across the screen and everything that it touches immediately opens up a text box, right? Maybe you want to be a little bit more intelligent, that your system will wait for half a second. If the mouse pointer stays there for half a second, that's the signal from the human that they're interested in that. If the pointer continues to pass over with constant velocity, don't open a text box, right? All those kinds of subtle things are really, really important. That make the difference between whether someone's going to be frustrated by that aspect of your software or engaged by it. Okay. Here's a somewhat dated example, but a nice one to illustrate this idea of supporting all of these three different kinds of interaction at the same time. Let's say we were writing a game for the Nintendo Wii remote here. So you have a remote in your hand, and you can use it, to point towards a bar that sits on top of your TV. There's an accelerometer in the Wii remote, and it can also sense, there's a camera in the Wii remote that can sense these two groups of lights that are on the bar by the TV. If the Wii remote combines that light information and that acceleration information, it can understand the relative position of the Wii remote from the Wii bar, and it can also understand the orientation of the Wii remote relative to gravity. Once you have that kind of feedback loop between the user, the remote, and the bar, you can create some fun things. So, physical interaction is pretty clear. The Wii remote with the bar is interacting and picking up this information. As I move the Wii remote, because of these sensors here, it detects change in position and orientation. Let's imagine we write a bow and arrow or an archery game for the Wii remote, where I hold the bar, I hold the remote, and I aim at the screen and then press a button which corresponds to. We can support the perceptual interaction by making a sound on the speaker on the remote, which is the sound of the release of the arrow, and then a short time interval later, we can emit the sound of the arrow hitting the target from the computer monitor or the TV. Right? If the Wii remote senses that the orientation is pointed away from the screen and I release the arrow, what is the human user expecting to hear? If I haven't aimed my arrow at the screen and I release the arrow from the Wii remote, how should this software system support my expectations about the sensory repercussion of my action?
Like you get off target or something.
Okay, so I should still hear the release of the arrow, right? I released the arrow, but maybe I hear a thud or I hear nothing, right? I missed the target. Okay, so maybe I released a few arrows and I get the idea of this interaction. I move further back and point at the screen and release the arrow again. Again, because of the thing in here, the prediction machine, what does your user expect to hear now? Should take longer, right? It seems kind of obvious, but it might take a moment to think about. You need to actually calibrate the time interval between the two sounds emitted by the Wii remote and the monitor based on the relative position of the Wii remote from the monitor, right? All of these design decisions that are now going to go into the game that we write are taking into account the physical interaction. I'm moving this thing. I can change its orientation. I can change its position. It's taking into account the perceptual interaction. I shoot an arrow. I hear it leave, and then I hear it hit a short time later. and conceptual interaction. I expect, once I've done this a few times, that if I shoot off target or I shoot from a further distance, I have a prediction about what I expect to hear. If I moved the Wii remote further away and I heard the arrow hit more quickly, it would be pretty frustrating, right? It would break my expectation of this system. Okay, I think we will stop there. You have a quiz due tonight. Deliverable 1 is due on Monday, and I'll put up the link for Deliverable 2 when I get back to my office. Enjoy your long weekend.